So in this video, we're going to talk about the three-phase full wave rectifier. And if you're anything like me, when I saw this, I thought, yeah, I think it's time to change my major. Now we're dealing with three sine waves instead of one. And the thing that popped into my mind is that's a lot of integration, but it's not difficult at all. We have the same period, same magnitude. So like before, we're going from 0 to pi to 2 pi, so one cycle. We're still going to be working with Vmax. This time we're going to look a little bit closer at the period. At this point, I'm assuming that you've already or are taking the AC to DC analysis course or have a good understanding of the unit circle. Between 0 and pi, we have pi over 2. And between pi and 2 pi, we have 3 pi over 2. So for a three-phase rectifier, we're taking the area under the curve for one sine wave. What that means is we can take the easiest one where sine theta is equal to 0. Because as you know, on a three-phase system, B phase would be sine theta minus 120 and C phase would be sine theta plus 120. So we're going to keep it simple and just go with A phase where it's just sine theta. So we can make things simple on ourselves and get rid of B and C phase. So what we're going to be doing is we're going to be taking the area under the curve between 60 degrees and 120 degrees. Basically what we're doing is we're going about the 90 degrees, 30 degrees on each side. I hope that's not confusing to you. So if you remember, we need to be in radians. So we need to convert the 60 degrees and the 120 degrees to radians so we can put those on our period. So I'm sure you remember how this works. To find radians, we multiply the degrees times pi over 180. Or if the angle is more than 180, we'll find the radians by multiplying the degrees times 2 pi over 360 degrees. So first we'll look at the 60 degrees and we want to find the radians. So we're taking the 60 degrees, multiplying that by pi over 180. The degrees are going to cancel out and that's going to give us pi over 3. Now to find the radians for 120 degrees, we multiply the 120 degrees times pi over 180. And again, the degrees cancel out and that gives us 2 pi over 3. So now we can bring that over and write that down on our period. So let's clean this up a little bit. What I like to do is I like to kind of put a border or a header over what it is that I'm actually solving for. That way I keep myself organized or else I'll lose it and mess things up really bad. So now that we have our parameters, we can go ahead and solve for the area under the curve between the pi over 3 and 2 pi over 3. Now keep in mind, for a three-phase system, each phase is going to give us the same value twice. So if we have two values per phase, we have three phases, that means we're going to have that value times 6. So to solve for VDC out, we have 6 times 1 over 2 pi times the integral of Vmax times sine theta between 2 pi over 3 and pi over 3. So taking the integral of this formula, we get VDC out is equal to 6 times 1 over 2 pi times the quantity of Vmax times negative cosine theta between pi over 3 and 2 pi over 3. So rewriting that, we get VDC out is equal to 6 times 1 over 2 pi times the quantity Vmax times negative cosine 2 pi over 3 minus negative Vmax times cosine pi over 3. So we can go ahead and pull out a Vmax and rewrite it. So we get VDC out is equal to 6 times 1 over 2 pi times Vmax times the quantity negative cosine 2 pi over 3 plus cosine pi over 3. Now we can go ahead and solve the cosine 2 pi over 3 and cosine pi over 3. Keep in mind we need to keep those in radians. So we solve and rewrite. VDC out is equal to 6 times 1 over 2 pi times Vmax times the quantity of 1/2 plus 1/2. This gives us the solution of VDC out is equal to 0.955 times Vmax. So I know the question might come in, when would I use something like this? And this is something that's used for variable frequency drives because we have a three-phase sine wave coming in, and then it's going through a full wave rectifier as part of the variable frequency drives. I mean, there's other parts in it as well, but that's you'll get into that in a different time. But I hope this helped. Keep chugging away. You got this.